readily available are scalar and vector control. So in case of scalar control, from the term you can understand vector and scalar. So vector means you can control two parameters, x and y, which is an imaginary part. Same concept. In case of scalar, it is going to be only magnitude, no direction or frequency. So scalar control is the most simple control where you can have a simple method of implementation and you can get a good steady state response. What is the drawback? You can't have a dynamic performance. Very sensitive speed control is not possible. Very sensitive speed control is not possible. Of course, you can't have a transients which are high when you're controlling the machine. So you can't have a very dynamically controlled performances. But it's a very simple method. Usually we adapt with reduced costs. What is a vector control? So vector control is a principle you can able to control the flux and torque separately. And how we can do that? We can do with some transformations. So these transformations are called as technically Planck's and Clark's transformation. The idea is to transfer the three-phase voltages or current to a two-phase quantity. So you will have a three-phase voltages which is having a phase difference of 0, 120 and 240 degree in real time from the grid, and these values can be transferred into two quantities, d, q, or alpha or beta. So if you are having a dq, then it's going to be a DC component. You are converting your AC components into DC components. If you are going to use Clark's transformation, you are going to retain the same sinusoidal characteristics as a two-phase component, but they are shifted by 90 degrees. So in this case, if you control the D, you can control the flux. If you control the Q, you can control the torque. Similarly, if you control the beta, you can control your torque. Alpha, you can control your flux. So this is the idea, simple idea, but looks simple, but the implementation is a complex. So how to do that? So most of the industries we use induction motor control most of the cases because it's much cheaper than DC machine, say 1/3 the price of your DC machine for the same power rating. But efficiency is not as similar to a DC machine because its construction is like that and it's an expensive machine. But for an induction machine, you can go up to 90% or 88% efficiency based on your power factor decides. So what are the possibility? The control of induction motor using V/F control method is possible. Vector control is possible. Direct and indirect vector control is possible, and field weakening control. So these are the different strategies we can able to adapt for an induction motor. How? Because you are going to have a stator part, you are going to have a rotor part. What are the possibility of control? I can control the supply so that I can able to control the flux, current, and voltage on the stator wind. So that is called stator control. If I'm going to do the same with the rotating part rotor, then it is called rotor control. Or third possibility, I have a stator and the rotor, and I have an air gap. So if I control the air gap, then it's going to be air gap control. So only three physical possibility to control any AC machine, either from the point of the stator, or from the point of rotor, or from the point of air gap. And about vector control, as I said, it's a very high degree of control for the speed and torque. And of course, you can have control as like a DC machine. You can be able to control the armature current and flux. Of course, you need to have a complete dynamics of the machine. Otherwise, we can't go for vector control. I mean, complete dynamics means you should know the complete theoretical equation which controls your AC machine. And the most important is that in case of induction machine, the stator and rotor are coupled by nature. So we are doing a decoupling by control algorithm. So in this case, we can't able to get a more closer application as like a DC machine, but we are trying to linearize it and to bring the performance as like a DC machine is our goal. And these can be done only by, as I said in the beginning, DQ alpha beta transformation. Simple control algorithm is shown here, how we can able to control your induction motor. So we have a three-phase induction motor, which is driven by a three-phase inverter from a DC bus. Nowadays, the technology is focused towards avoiding sensors. Without sensing the rotor speed, how we can able to control the AC machine. So we have algorithms. The algorithms is given by the formulas which controls the AC machine. So I don't want to give you a very high theoretical background, so the session will become not interesting. So we try to get the two parameters of the current from the phases which is given to the three-phase induction machine. And here we can able to calculate two parameters. One is what is the flux linkage in your rotor by equations. Of course, we can able to calculate what is the rotor speed. So this all can be done by if you know the exact dynamics of your electrical induction machine. Then this is another block also we are using to calculate these two-phase components or three-phase components into alpha beta. So it's going to be a flux transformation. Same three-phase voltage. What is the difference? Here you will have 0, 120 and 240. Here it's going to be only 90 degree. So both will be sine wave, but they are shifted by 90 degree. Then we are going to use again a Parkes transformation. These AC quantity will be converted into DC. So both are the same. Only the difference is here you are going to have AC components. Here you are going to have DC components. Now how the control algorithm looks. So I need to control the flux. I need to control my speed. So this is the reference value of the speed, omega r, which is required to drive the motor. And this is the feedback taken from the calculations from the real parameter of the currents and voltages, then fed to a error amplifier. What is the purpose of the error amplifier? It will find the difference. I want 1450 RPM. And this is the feedback. Initially, the motor starts with 0, then it reaches slowly. So I will have the feedback. The error is calculated. The error is given to a PI regulator. What is the purpose of this PI regulator? Is to find and track the set speed. Usually, when you're feeding an input to your PI regulator with voltage, because in real time, these parameters are given as a voltage. So here I will have a parameter as a voltage. When you feed voltage as an input to the PI regulator, obviously your output should be a current. It's like V is equal to IR indirectly. So you have a reference current which controls directly your torque. And this is compared with the actual torque producing current from the calculation. Then again, I give you another PI regulator which is able to track the reference current of your torque and produces a voltage signal which is equivalent to your torque producing voltage. Similarly, second part, I am going to fix the value for your rotor flux. The feedback is taken from the calculation and given to a PI regulator. So here again, I am going to have a voltage value, which is a difference between the actual rotor flux and the feedback rotor flux, and given to a PI regulator. So obviously the input is a voltage, output is going to be a current, which is compared with your actually estimated or calculated value from the machine, so that it can be compared and you can able to get a error. Again, I am going to put a PI regulator. The purpose of this PI regulator is to track the value of the current, which is a reference for your flux. So the output is going to be a voltage again. So this is a reference voltage signal for your flux producing component. Now we can adapt inverse clock transformations, so that all these inverse clock transformations, so the clock transformation, so that all the DC components. So here I will have a signal on DC. This DC will be converted into AC value through this transformation. So same parameter. Here it will be DC. Now I'm going to have a AC components. So these AC components are given to the space vector modulations. The space vector modulation has been carried out, and all the 6 PWMs which is required for the inverter is given, so that I can able to drive the inverter for the required speed control of the motor, which is driven by the inverter. So driven by the inverter. So whatever the speed I give you, whatever the flux I given, the same value the motor will drive. So based on the information of your flux and speed. Someone can able to, because it, for example, this is disturbing me a little bit with my presentation. Could somebody, yeah, okay, thank you. So now I can able to control the speed of your motor. Meantime, the most important parameter is all these transformation is done based on the angle of your rotation. So the angle of rotation of your speed of your rotor depends on how much angle. So we don't know what is the angle which the rotor is rotating. This angle can also be calculated in the block, which is given by this eta s. How to calculate this eta is the most simplest solution without having any complex idea is you have the two parameters, alpha and beta. So we know when we have a real and imaginary part, of course, if you want to calculate an angle,